All right, we're going to start Unit 5, and as I've mentioned in our class meetings, Unit 5 is more like Units 1 and 2. So we're moving away from organic chemistry, and we're getting back into the inorganic chemistry. So we're going to have a lot more math in Unit 5. We're also going to see polyatomic ions again. So remember the carbonate, bicarbonate, sulfate, sulfite, phosphate, all of those are going to be seen quite often in Unit 5. So I definitely would suggest reviewing your polyatomic ions. It will help you in the long run. You are also, while you're reviewing your polyatomic ions, you're preparing for the final, which isn't that far away now. So we're getting towards the end of the semester. So for Unit 5, definitely review those polyatomic ions. Also, have your calculator handy and your periodic table. So we're going to be using those items again. Units 3 and 4, we didn't use the calculator, really have to use the periodic table, but have those nearby because we will definitely be using them soon. So to start off in Unit 5, we're going to talk about solutions. And water is the basis of all the solutions that we're going to be dealing with. So we're going to talk about water-specific properties. Now, remember that water is H2O. And if you remember from Unit 2, we learned how to draw Lewis dot structures. And we learned that, the octet rule, all of that. Now, hydrogen, is it a metal or a nonmetal or a metalloid? It's a nonmetal. So nonmetal. Oxygen is also a nonmetal. So what type of bonding holds water together? It's covalent. So this is a covalent compound. Now, we can break covalent down further. Remember, we talked about nonpolar covalent or polar covalent. Well, before we start talking about the specific types of bonds in water, let's just draw the Lewis dot structure of water. So remember that hydrogen can only have one bond. Let's just fill in the valence electrons for oxygen. Oxygen has 6 valence electrons. So it bonds to 2 hydrogens in order to achieve an octet. So this is what water looks like. Remember that hydrogen can only have one bond, and that's why its structure is this way. Okay, so we know that this bond right here is covalent because you have 2 nonmetals sharing electrons in order to achieve an octet. Now, can you tell me, is it polar covalent or nonpolar covalent? Remember that concept, polar covalent or nonpolar covalent, deals with electronegativity. As you go from left to right in the periodic table, you increase the electronegativity. As you go from the bottom of the periodic table to the top of the periodic table, you increase the electronegativity. So you have hydrogen over here, and you have oxygen over here. There is a difference in electronegativity, so this is going to be a polar covalent bond. Oxygen, if you look this up, is more electronegative, so it's going to hog the electrons in this bond. So it's going to get a partial negative, while hydrogen has a partial positive. So it's a polar covalent bond. The polarity of this bond is what I've just labeled. So we've talked about water, talked about the structure of water. Now water has a unique type of bonding that goes beyond polar covalent bonding. It's called hydrogen bonding. And because of hydrogen bonding, water has some very unique and useful properties. So hydrogen bonding gives rise to a high boiling point, and high surface tension. So, those bugs that walk on water, they wouldn't be able to walk on water if it weren't for water's hydrogen bonding. So, very, very unique. So, what exactly is hydrogen bonding? Well, it's not polar covalent bonding. It's not covalent bonding. It's beyond that. So, I'm going to draw some water molecules out. So I'm just going to have a few like this. And then if you have a snow day, you can just fill up your paper with waters and draw out hydrogen bonding if you wanted to, if you didn't have anything else to do. All right, so I have 4 water molecules. I told you that water exhibits hydrogen bonding. Hydrogen bonding, I'm going to give you the definition and then we'll label it, is the attraction between a hydrogen atom bonded to an electronegative atom, En for electronegative. So the attraction between a hydrogen atom bonded to an electronegative atom, and that electronegative atom could be oxygen, nitrogen, or fluorine, and another nearby oxygen, nitrogen, or fluorine atom. All right, so let me read this definition again. The attraction between a hydrogen atom bonded to an electronegative atom, oxygen, nitrogen, or fluorine, and another nearby oxygen, nitrogen, or fluorine atom. That's clear as mud, right? Not a very explicit definition. So let's go through these waters that I've just drawn, and hopefully we'll clear some of this up. Okay, I'm going to draw their polarities above them. So remember that the oxygen has a partial negative, hydrogen has a partial positive, partial positive, partial negative, partial positive, partial positive, partial negative, partial positive, negative. Okay. All right, so let's look at this definition again. The attraction between a hydrogen atom bonded to an electronegative atom. I'm just going to pick out a hydrogen atom that's bonded to an electronegative atom, oxygen, nitrogen, or fluorine. So this hydrogen atom fits the bill. Now, it is attracted to another nearby oxygen, nitrogen, or fluorine atom. So what we're describing here is the attraction between this hydrogen that's on a different water molecule and the oxygen on another water molecule. And you can see why opposites attract, right? You have a partial positive on the hydrogen and a partial negative on the oxygen. So this purple line that I have here, that is hydrogen bonding. And you can label it in so many other places with these waters. So any time you see a hydrogen and then a nearby oxygen atom, you can fill that in. So now, perhaps by drawing out these purple lines, you can see how if you had a paper full of water molecules, you could just draw out hydrogen bond upon hydrogen bond. But this hydrogen bonding is unique to certain molecules, and it gives rise, since these bonds, these attractions exist, that's why the boiling point is so high. It's because it takes so much energy to break these bonds, because these oxygens and hydrogens are so attracted to each other, you have to put a lot of energy in order to get it to go from a liquid to a gas. And that's also why you have high surface tension. So, I'm going to go over a few examples of molecules that may or may not have hydrogen bonding. So I'm going to ask you a question. I'll do this in a different color. Which of the following can have hydrogen bonding? Okay, so I'll put A, CH4, B, HF, C, NH3, and then D, let's do HCl. Okay, so if you were asked a question like this on an exam or a quiz, you might be very intimidated. There's a shortcut to this. If you think about the definition of hydrogen bonding, first and foremost, you would have to have hydrogen in your molecule. So, have your checklist. Do you have hydrogen? Well, let's see. A, B, C, and D. All of these have hydrogen, so we're not going to get off that easy. The next step would be to look for electronegative atoms. So do you have O, N, or F present? Because if you don't have those atoms present, you're not going to have hydrogen bonding. So if you look at A, we do have hydrogens present, but we don't have O, N, or F. So that one's off. And if you don't use this shortcut, your alternative would be to draw the Lewis dot structures, and it could take a lot of time. So first, keep it simple. Does it have hydrogen? Secondly, does it have oxygen, nitrogen, or fluorine? So B has hydrogen, and it has a fluorine. So this could have hydrogen bonding. C has hydrogen, and it has an electronegative atom, nitrogen, so this could possess hydrogen bonding as well. D, we have hydrogen, but we don't have O, N, or F, so that's wrong. And just to show you HF, this is what your Lewis dot diagram would look like. You have the partial negative here, partial positive here. If you had another HF, you could imagine how you would have hydrogen bonding based on what we just learned. NH3, N has 5 valence electrons, hydrogen has 1. So you have partial negative here, partial positive here, positive, positive. So you can also see what the polarity is in NH3. So hydrogen bonding is very important. And we see this all the time in water. Since water is the basis for all our solutions in Unit 5, it's an important concept to discuss. So on the next page, I have a definition, a space for solution. And solution is defined as solute plus solvent. So the solute is the smaller amount. Most often it changes phase, whereas the solvent is the larger amount, doesn't change phase. So you're probably thinking solution, solute, solvent, all these terms, they don't really make sense to me. I can't apply this. Well, let's say you're making Kool-Aid. Kool-Aid is a solution. So let's say you're making watermelon Kool-Aid. That is your solution. Another term for solution would be mixture. Okay, so if Kool-Aid is your solution, and you made up your, let's say you're using the sugar-free Kool-Aid mix, so you don't need to add the sugar. You just need to add the powder, and you add this to water. Which is your solute and which is your solvent? Well, the powder would be your solute. So solute would be your powder. Your solvent would be water. So for this Kool-Aid example, your powder goes from solid to liquid. That's what I mean when I say changes phase. It goes from solid, that powder, to a liquid. Now, like dissolves like. We've heard this before, but I just want to reiterate this. Polar dissolves, polar or nonpolar? Polar. And then nonpolar dissolves nonpolar. So when you have an ionic compound and you dissolve it in water, first of all, let's step back a minute. What is an ionic compound? Well, it's not covalent, it's ionic. Covalent is non-metal to non-metal. Ionic is metal to nonmetal. So when you have an ionic compound and you put it in water, what happens? Now, ionic compounds, by the way, are for the most part soluble in water. So let's say we have just a general ionic compound. I'm going to say it's M and M, metal, nonmetal. So you have your metal, and remember that metals lose electrons. This is a great review of Unit 2, by the way. So if a metal loses an electron, is it going to have a negative charge or positive charge? It's going to have a positive charge because it's short an electron. So it loses an electron. The nonmetal gains this electron. So is it going to have a negative charge or a positive charge? Well, if it has an excess of electrons, and remember that electrons have a negative charge, then it will have a negative charge. So you have these charges in ionic compounds. The metals have positive charges, the nonmetals have negative charges. And they're very soluble in water. And think about water again. This is what water looks like. And it has this polarity. You have the positive, positive, negative. If you have a lot of water molecules that are gathering around the metal ion, the positive ion, which part of water will be attracted to the positive metal ion? Will it be the oxygen which has a partial negative, or the hydrogen, which has a partial positive? Well, the oxygen will be attracted because it has this. So you're going to have your water molecules aligning themselves around these metal ions, these cations, because of the polarity of water. So that's what makes them so ionic compounds so soluble. So depending on the metal ion, you could have 10 water surrounding it, you could have 6 water surrounding it. A lot depends on what metal you're dealing with. If we look at the nonmetal, how will water align itself? Will the oxygen be pointing to the nonmetal? No. The hydrogens will be pointing to the nonmetal because they have a partial positive and they're attracted to that negative. So again, you can just imagine all these water molecules surrounding this anion with the hydrogens pointing inwards. So that was a cat, sorry. This phenomenon is called hydration. So hydration is what we've just talked about. Now, by and large, ionic compounds are very soluble in water. We are going to learn that the majority of ionic compounds are soluble in water, and when they're soluble in water, this is what happens. There are some exceptions. There are some insoluble ionic compounds, and we'll talk about solubility rules coming up. But by and large, when you have an ionic compound that is soluble in water, this is how the water molecules surround the ions. Okay, so we talked about solutions. We're going to be talking about solutions quite a bit in Unit 5. For A, B, and C, I want you to identify the solute and solvent in each solution. So think about what we learned. The solvent is the larger amount, the solute's a smaller amount. So for A, 50 grams of silver and 4 grams of mercury. The silver is in the larger amount, so it's going to be the solvent, and the mercury is going to be the solute. B, we have 100 ml of water and 5 grams of sugar. We'll say that density, just to repeat, of water is 1 gram per milliliter, so it's the same as 100 grams. So you have 100 grams of water and 5 grams of sugar. So water will be the solvent, sugar will be the solute, and then the last one, 1 gram of iodine and 50 ml of alcohol. The smaller amount, way smaller amount, is iodine, so this is going to be your solute. This will be your solvent. So alcohol is your solvent, iodine is your solute. So for this section, if it's not explicitly stated, assume your solvent is water. So we're going to be dealing with water-based solutions quite a bit unless it's otherwise explicitly stated. So I will stop the lecture here. I know it's been a lot of information and we haven't covered many pages in the packet, but I want you to get in the mindset of Unit 5. You really are reviewing a lot more than you realize from Units 1 and 2, and you're getting prepared for not only the Unit 5 exam, but also the final. So if you work hard in Unit 5 to catch yourself up if you've forgotten some stuff from Units 1 and 2, it will pay off in the end. You won't have to study as hard or cram as much for the final. So, if you really try to aim for an A on this Unit 5 exam, I think you might be pleasantly surprised by how much it helps you studying for your final. So, for now, I want you to do the homework problems that are covered, that we covered in this lecture. I also, the lab that we've talked about some of it, the concepts in the lab. Lab 19, graphing solubility. We're starting on some of these concepts. So you can start to look at that one. If it doesn't completely make sense, hold off until a few more lectures. But we have a lot of labs that you can work on outside of lab this coming week. So, just be kind of flipping through them, see if anything jumps out at you, try to answer some questions. You can always go back and erase and change your answers. It's not set in stone. You haven't handed it in yet. So, until next time.